Probability of independent and dependent events. In this lesson, we'll find the probability of independent and dependent events. Let's take a look at this example. The television meteorologist said that there was a 50% chance of rain on Saturday and a 25% chance rain on Sunday. Janice was upset because the ninth grade at her high school was planning their class picnic for Saturday and the rain date was Sunday. She thought that the probability for rain on Saturday and Sunday was 75%. Kiona, on the other hand, said that the probability of rain on both days was just 12.5%. So, who was right? Okay, we know how Janice found her answer. She got 50% rain on Saturday and 25% rain on Sunday. She added both of them, which ended up with 75%. Kiona said that the probability of rain both days was just 12.5%. How did she come up with this answer? And let's find out who is more correct. Okay. In this case, we can also simulate the situation above using manipulatives. This could be done by tossing a coin and spinning the spinner at the right 50 times. Tossing a coin will give you two possible outcomes, and each time you want to find the probability of getting heads or tails, that's 50%. And at the same time, when you spin a spinner like this one, which one is blue, the other three are red, this also represents 25%. Tossing a coin will represent your 50%, the spinner will represent your 25%. So every time that the arrow will land on the blue part of the spinner, okay, that will represent our 25% chance of rain. Okay? So does the outcome of tossing a coin affect the outcome of spinning a spinner? Of course, the answer is no. When you toss a coin, there is no way that can affect the outcome of spinning a spinner, and vice versa. When you spin the spinner, there is no way that it can affect the outcome of tossing a coin. Okay? So the answer to that question is an emphatic no. Okay? The weather situation and the activity above is a good example of independent events. Events are independent when the outcome of one event does not influence the outcome of the second event. And if we use the fundamental counting principle, okay, we know that there are 2 times 4 or 8 possible outcomes of tossing a coin and spinning a spinner. Of the 8 outcomes, there is one pair, okay, heads and blue, that matches the meteorologist's prediction. Okay, so if you toss a coin, it ends up heads, that's a Saturday chance of rain. If you spin the spinner and it lands on blue, that is your Sunday chance of rain. Okay, so 50% rain on Saturday and 25% rain on Sunday. Let's determine the probability. Okay, we know that the probability of getting heads and landing on a blue is equal to the number of ways heads and blue can occur over the total number of possible outcomes. We know that there's only one way heads and blue can occur, and there are 8 possible outcomes, so the probability is 1 over 8. Okay, now we know that the probability of heads is 1/2, the probability of 2 is 1/4. So to be able to get 1 over 8, we can also multiply 1/2 times 1/4, which is 1 over 8. Also the probability of getting a heads and a blue. Okay, this points us to the fact that the probability of 2 independent events is the product, okay, is the product of the probability of each event. Okay, which brings us to a general rule in the probability of 2 independent events. Okay, it can be found by multiplying the probability of the first event by the probability of the second event. Okay, so in symbols, the probability of A and B is equal to the probability of A times the probability of B, given that A and B are both independent events. Okay, so how does this work? Let's take a look at example number 1 and see how this works. In a popular board game, you go to jail if you roll 3 doubles, okay, in a row. What is the probability of rolling 3 doubles in a row? So every single time you roll a pair of dice, okay, when you roll that pair of dice, the next time you roll that pair of dice, the outcome of the second roll will not affect the outcome of, the outcome of the second roll will not be affected by the outcome of the first roll. Okay? And at the same time, the outcome of the third roll will not be affected by the outcome of the first and second rolls. So this is a good example of an independent event. Okay? Because of what I just mentioned, they do not affect the outcome of the next roll. There are 6 ways to roll doubles: 1 1, 2 2, 3 3, 4 4, 5 5, and 6 6. Okay? And there are 36 ways to roll dice. Okay? How do we know this? Because according to the fundamental counting principle, one die, okay, will have 6 outcomes. So the first die will have 6 outcomes. The second die will have another 6 outcomes. Multiply that and you end up with 36. That's how you get 36 ways. Okay? Thus the probability of rolling doubles on the toss of a die is 6 out of 36 because of these 6 outcomes: 1 1, 2 2, 3 3, 4 4, 5 5, and 6 6. 6 out of 36, or 1 out of 6. Okay? That's one way of analyzing it. And the other way is, okay, using the formula for finding the probability of 2 independent events. Okay? In this case, 3 independent events. So, the probability of getting doubles on 3 rolls would be the probability of doubles on roll 1 times the probability of doubles on roll 2 times the probability of doubles on roll 3, which is basically 1 6 times 1 6 times 1 6, okay, which is the same as 1 over 216. Okay, so that's how you find the probability of rolling 3 doubles, okay, in a row. The probability of rolling all doubles in 3 rolls of a dice is 1 out of 216. Okay, so that's a good example of of independent events. Another concept that we need to learn here is the opposite of an independent event, which is a dependent event. Sometimes the outcome of one event affects the outcome of the second event. When this happens, the events are called dependent events. For example, suppose you choose a card from a deck, keep it, and then your friend chooses another card. Since you did not replace your card, your friend has fewer cards from which to choose. These events are dependent. So when you talk about getting a card from a deck and you don't replace that card, okay, and you choose again, that is a good example of a dependent event, because the second, okay, outcome, okay, is dependent on the first one. Okay, so in words, if 2 events A and B are dependent, then the probability of both events occurring is the product of the probability of A and the probability of B after A occurs. So in symbols, the probability of A and B is equal to the probability of A times the probability of B following A. Okay, this looks a little foreign to you right now, and let's take a look at example 2 and see how that clears it up. Okay, bag lunches are prepared for 50 students on a field trip. There are 3 different desserts in the bags. 20 bags contain a brownie, 15 contain a chocolate chip cookie, and 15 contain an oatmeal raisin cookie. The bags are arranged in random order. Connie and Tail were the first and second in line. what is the probability that Connie and Dale both select a bag containing a chocolate chip cookie? This is a classic example of a dependent event. Why? Because as Connie chooses her bag, okay, there will be one fewer bag to choose from when Dale gets her turn to choose her lunch bag. Okay? So for Connie to choose a chocolate chip cookie, it will be equal to the number of bags containing chocolate chip over the total number of lunches. So we know for a fact the number of bags containing chocolate chip in this case would be 15 right here. It says it specifically here that there are 15 contain chocolate chip cookie. Okay, so that would be 15 out of 50. Why 50? Because there are 50 total lunch bags, okay, available. So 15 out of 50 or 3 out of 10. So when Connie chooses first, her probability of being able to choose a chocolate chip cookie is 3 out of 10. Okay, and then let's discuss Dale. Well, let's assume that Connie chooses a bag containing a chocolate chip cookie, of course. Okay, now on the second part of this problem, for Dale to get the probability of choosing a chocolate chip cookie in the bag, that will be equal to the number of containing chocolate chip left, okay, over the number of lunches left. Okay, so it's not anymore 50 lunches, it's not anymore 15 bags. Let's say Connie chooses one, this becomes 14 bags, and the total number of lunches will be 49 bags. So it'll be 14 over 49, or 2 over 7. Okay, and from there, okay, we combine what Connie got and Dale got. So the probability of choosing a chocolate chip cookie in a bag for both of them will be equal to 3/10 times 2 over 7, or the probability of A times the probability of B after A. Okay, so probability of B following A, which simply means that this is the probability of A, Connie choosing a chocolate chip cookie, times the probability of Dale choosing a chocolate chip cookie after Connie has chosen her bag. Okay? Answer would be 6 out of 70. Simplest form would be 3 over 35. So in this case, the probability of both of them getting a chocolate chip in their lunch bag is 3 out of 35. Okay? And those are examples of independent and dependent events. Lessons done. On Google Forms, type a summary of what you've learned by responding to the objective of the lesson, and type a question you might want to ask in class. Thank you.